go. Cool. All right. Well, thank you for turning up in the morning. I know it's hard. Anyways, today we're going to talk about relation database management querying. Specifically, we're actually going to look at the fundamentals of how it's been formed in the first place. So, because relational database management system is actually based on a relational model, which is effectively a mathematical model that's been basically invented by a mathematician. So effectively everything around that is based on the first order predicate logic, and underlying querying itself, not surprisingly, is also based on the predicate logic. Predicate logic is basically being the procedural execution of queries. So we're going to look at the relational algebra and look at the SQL that makes this use of relational algebra meaningful to us, meaningful to programmers basically, or for developers. So it makes a relational model more or less accessible to pretty much anyone. Okay, so first of all, relational model itself, which SQL Server is based on, has got some basic logic, how it actually executes the queries, how it actually gets the data, how it writes the data, etc. So all the mechanicals of the SQL Server aside, there is a fairly simple mathematical logic of how it actually searches for data, how it joins the data together, and how it produces the results. So this is exactly what we're going to be looking today, is called relational algebra. There are two actually variations with relational algebra and relational calculus, which is exactly the same thing. It's just calculus a little bit smarter for those people who don't like the word algebra, I suppose. Okay, so if we break those two concepts down, basically relational algebra and SQL, relational algebra is a procedural language. It's a procedural theoretical language. It's just a way to express how you want to retrieve the data from a specific sort of sets of data. And SQL is actually a usable language, I would say. It's something that we can actually talk to. Well, it's almost like we're giving instructions to the relational database management system in a meaningful form, but then those instructions being translated into relational algebra, relational language. And we're also going to have a look at how it actually translates those commands, such as select something from something, etc. So the things to take away from this specific slide, or this specific 5 minutes of basically talk, is the fact that relational algebra is not procedural, just theoretical language. It just helps us to actually understand how how we can query the relational database. And SQL is something that I actually use to actually query it. Okay, to actually grasp the whole concept, we're actually going to look at a very simple. Well, first of all, we need to define the different terms within the relational algebra, because they are a little bit different to what we got used to. So, because relational algebra is basically a mathematical model, so everything that we know about, basically every term that we use in it sounds a little bit different, but it's not very difficult, effectively. So, we know about basically a table in SQL Server, or in SQL. In the database management system, we've got a table that contains data. So this table actually in relational algebra, and basically in the actual relational model, is called a relation. The reason why it's called a relation is because it contains data in relational form. So for example, each row contains data that are all interrelated. And then the table itself contains rows that also relate to a specific domain. So for example, products. That table contains only products and definition of those products. And each row contains basically information about a specific product. So that's why it's called a relation, effectively. So that's a relation of different concepts of data. That relation itself, which is basically a table, contains attributes. Attributes, we know them as columns or data fields. A table, or a relation in our case, has got a degree. So degree is a number of attributes that data relation has got. So basically number of columns. And it's got cardinality. Cardinality is number of rows that that relation has got. So in this specific lesson, I'm going to be referring to a table as a relation. I'm going to refer to columns as attributes. Number of columns I'm going to refer to as degrees, and number of rows I'm going to refer to as cardinality. Also, a relational model has got a concept of a domain. For basically each attribute has got a domain, which effectively what kind of values you can store. So it's allowable fields, or effectively if it's a constrained field, it's a range of fields that it can have. For example, in our case, the attribute name can contain anything that is string, basically any varchar of maximum field 255. So that's effectively a domain. And overall, the domain of the table is going to, well, the domain of the relation itself, what sort of data you can actually contain within that table, or within that relation. And normally in the relational model, we have each basically relation, each row would have some kind of unique identifier that uniquely identifies that row. So it's a primary key, for example. And that primary key in another table has got a foreign key, so that we can then join those two tables together. And again, in the relational model, we don't call rows as rows, because it's basically a set of data. We call them a tuple, or tuple. I like tuple, so we're going to call it tuple. So basically, tuple, I think, is a definition of that word is basically a collection of different related data. So again, everything is related. That's why it's called a relation, and each row is called a tuple, basically. So, all right. So to better kind of represent the whole relational model itself, we kind of have to look at a very basic concept of Cartesian. Well, basically, we have to represent that thing, relational model, somehow, so that we can all understand it more or less. And the easiest way to do this is to use a very basic math and a concept called Cartesian product. Have you heard of Cartesian product? Well, this guy has, because he has a math degree. But effectively is where you multiply two things together, effectively. So imagine we've got a data string, well, not data string, we'll call it data set, or just set of numbers, 1 and 2. And we've got another data set of data, 3 and 4. And that cross basically means that we're going to produce a Cartesian product out of those two sets of data, well, sets of numbers. And the way we do this is basically we take the first number from relation 1. Well, this is, I basically represent this D1 as relation 1. Relation 1 contains two sets of numbers. Well, one set of numbers of basically degree 2. And we take the first number 1, and then we basically combine it with set number from the second set. 1, 3, then 1, 2, and then from the second set 2, we take 2, 3, 2, and 4. So we're going to get something like this as a relation. So if we're doing a Cartesian product of two sets of numbers, we basically just multiply them together. Well, not multiply them in in algebra terms, we just basically combine them together. We get a set of data that looks like this: 1 and 3. So 1, 3, 1, 4, 2, 3, 2, 4, and so on. So we basically merge those two sets of data together. So that's called the Cartesian product. Where I'm going with that is, where am I going with that? Yes, so effectively, if we take two sets of data and we perform any kind of mathematical function on it, well, logical function on it, such as Cartesian product, we're going to get so-called a relation. So we're going to get another result, and we refer to that result as a relation again, because all those numbers are related. Okay, so what we're going to do is actually going to go on SQL Server itself, and we're going to run a very simple sort of representation test of it. Where is my lesson? There you go. Okay, so what I'm going to do is I'm going to declare two sets of data, D1 and D2 as the temp tables. I'm just going to insert those two values in each one of those tables. And I will basically produce a Cartesian product using SQL. So just to represent what that D1 table and D2 table looks like, I'm just going to go and select all the data from it. And effectively D1 contains 1 and 2, D3 contains 3 and 4. And to do a Cartesian product in SQL, we just join those two tables together using so-called cross join. Remember, the Cartesian product basically assigned for Cartesian product is a cross. Basically, this is what we're doing in SQL. It's just basically cross join those two tables, and we don't get a result. So we get a result like this. So every value from table D1 is basically merged with D2. Well, not merged. It's a different word. It's basically, how do I say it? It's been joined. So we jump back to our where was I? There. So that relation itself that we produced using that Cartesian product is a relation, and it's got a tuple, which is a row, and we've seen this in SQL. It's got a degree, 2 field, 2 attributes, and the number of those rows is basically our cardinality. We can also set some conditions when we actually run a Cartesian product. So we can say, okay, we will do Cartesian product of those two sets of data, but then we only want to actually we only want to select the data where specific conditions are met. So for example, in this case, I'm saying that relation 1 would be equal Cartesian product of D1 and D2, where value of D1 equals 3. So let's jump to our SQL again, and here I can actually start typing where D2 table. This is basically so because y is a value of D2 relation equals 3. So I'm now basically limiting V2. Now I'm limiting the data that I'm getting back out of that Cartesian product only to values where the second value equals 3. And by the same token, I can use different I can use the attributes of the first table to kind of refer to the second table, pretty much exactly like this, where the value of the second relation equals the value of the first table plus 1. Something like this. If I run it, I only get value of the first table plus 1 equals 3. So that's basically the result that I'm getting. Okay, let's move to actual relational algebra. So effectively, if we just basically think about it, everything that happens underneath the SQL server, under the bonnet, is basically all your SQL queries are being translated into query execution, which is effectively has taken its beginning from relational algebra. So pretty much everything that happens under the bonnet in SQL server is relational algebra, in the sense that it actually runs all the commands procedurally, scans the tables, merges them together, and then joins them together, pretty much using the relational algebra algorithms. It's a little bit more complicated from an optimization point of view, but that's the theory. In relational algebra, we have several things that we can actually do, and these are just some of them, but pretty much this is the major major ones that we actually use on a day-to-day basis. So if we can do a selection. A selection is we have a table and we want to get the data out of it, basically. That's about it. In relational algebra, it's called restriction, simply not to confuse it with selection in SQL. Restriction means that we're going to take the whole relation, all of the data in that relation, and we want to take some data out of it based on some conditions. So with a restriction, you can run a relational algebra query effectively without any kind of restriction, without any condition in that restriction, but restriction itself becomes the actual table itself. So this is the range where you're going to be getting data from. Then we have a projection, we have union, join, intersect, and divide. So each one of those we're going to look at individually. Okay, selection and projection. Projection sounds cool, but it's not really cool. It's just basically something very simple. But we're going to look at selection first. And selection, remember in the previous lesson, we looked at predicate and subject. So first order predicate logic. Predicate being a condition and subject being what we actually selecting from. Subject being our relation and predicate is being the condition of basically our formula that we'll be using to select the data from that table, from that relation. And effectively, selection is you take specific rows out of specific tuples from a relation. And in relational algebra, there's a simple, there's basically a formulation for a selection with that. What's that sign called? That's not omega. That's something. That sign with a line at the top, where A and B are attribute names. Attribute names being basically our columns in our table. Then binary operator, for example, less, more, equals, and so on. In SQL, we've got other commands such as like and basically your varchar functions, etc. Then the value constant is what we actually compare it to. Value constant can also be an attribute. And then in brackets, this is our subject, is actually a relation. This is actually a table that we're selecting from. So, for example, if we write in relational algebra a formula like this, definition like this sign, then the actual predicate itself will be days to manufacture, for example, more than 2 out of a relation called product. We're going to get some data out. So this is how we write it effectively to define what sort of data we want out of product table. Okay, let's jump to SQL. And for this specific demonstration, I'm going to be using AdventureWorks database, which you can download from the internet and basically install it to your SQL Server Express. That's the database that contains some sample data, and we can run some queries on it, etc. It's not fully, it's not in the third relational form, that data, but it's more or less looks like a production database would look like for some sort of business. So it's a really good kind of example data or sample data set. And we're going to be using that database to run some queries against, and further down on all the lessons we're going to be using exactly the same database. Okay, so what we want is we want to select all the rows where days to manufacture more than 2 out of product database, out of product table. So we basically in SQL we write select, which is identifying that we want a selection basically routine to run from. This is basically from being our relation, production product, and now our predicate we specify in a where clause, where predicate days to manufacture more than 2. So more being our binary operator and 2 being our value constant. And at this time, I'm just going to specify we want all the fields by putting the star after select. If we run it, we only get rows. Well, basically, we only get tuples from the from product relation, where days to manufacture more than 2. If we find an attribute called day to manufacture, you can see that they all just returned more than 2. Not very complicated. I'm pretty sure that everyone have done this or a similar thing in the past. Okay, so projection, on the other hand, in relational algebra basically refers to what attributes you actually want to get out of a relation. So you normally use projection with the relation. And in relational algebra, it refers to this Russian letter P, and then you specify all the attributes you want to select out of the relation. So for example, if I want to select only product and product number out of product's relation, I would write a statement like this. So there's P, then product ID, product number out of product relation. And then I can use that to basically to only retrieve the data that I actually need. Okay, so let's jump to SQL Server and then limit our selection to product ID and product number only. So we only get those 2 attributes being returned. Why is it important? Well, it's important to kind of understand how SQL Server and any actual relational management or relational database management system, decompiles this query. So if we then look at the next example, the union, for example, then we will notice that in order to, I'll jump back to this, in order to retrieve this product, well, this attributes, what's actually happening, it treats the product relation as a whole data range, then runs the query on it. First thing that happens is we run the selection query on it, returns us a relation that contains all the columns, all the attributes out of a product relation, and then strips all the things out of it, like all the things that we don't need, and leaves only the attributes that we do need out of projection. So, for example, the first thing that it does, it runs the selection or restriction, and then it runs, well, basically it runs. The next step is out of that relation, it takes basically returns only the attributes that you need that you specify in projection. So the whole idea behind basically looking at the relational algebra and SQL at the same time in parallel is to sort of give you that idea that everything underneath, or under the bonnet in SQL Server runs procedurally. So all these queries are being effectively not decompiled, but they're being processed into a procedural language. Okay, so the next operator I want to look at, I think they're called operators, is called union. And the union effectively is taking 2 relations and combining them together. So in the output relation, you get data sets that are in both relations. So you just basically combine them together. So, and this is what I'm talking about. For example, we can represent the first selection that we've done, where we're selecting, well, all the products from a product relation where days to manufacture more than 2, but in our case, we're going to select everything that has got days to manufacture equals 1. Then we're going to dump it into a viewing relation. And then out of that viewing relation, we're going to output only the product attributes that we need. So product ID, product number, and a name. And we're going to get something like this. Then we're going to union it to another selection, where again, we're going to select only the products that contains color equals black, dump it in the viewing relationship, in the viewing relation, and out of that viewing relation, we're going to basically output exactly the same number of columns, product, product number, and a name. We're going to get a table like that. And then we basically join them together. Well, not join them together, we union them together. So we get all the results out of this table, and then underneath we append all the results, all the tuples from this relation. So if we look at specific rows, we can see the 2 rows from the first relation, followed by a row from the second relation, and so on. So that's a union. And to look at the union, basically what I'm going to do is I'm actually going to write a query that represents our first selection, which is that one, where I'm going to select all the products out of a products database or products table where days to manufacture equals 1. So that's that query. So again, this is the relation name, this is our predicate, and this is the attributes that I want to select. So I'm getting all those attributes selected out of the product relation. The next one, I want to write another query that will return us all the products that has got color black in their attributes. And again, I want to produce exactly the same attributes as an output: product ID, product number, and a name. So I'm just, instead of writing it, I'm just going to go and grab another query that I've written. So it's that, again, from product relation, where color attribute equals black, and then I'm outputting those attributes out. So if I run them separately by selecting in SQL Server, in SQL and Server Management Studio, a specific part of the query that I've written and running it with F5, I'm just getting that result out. So in this output, I'm only getting products with where basically color is black. And then what I can do, I can run them side by side. I do 2 tables in the result set. Let's add the properties. And then I can union them. So I'll put union in the middle. Something like this. So basically, first selection, second selection, union in the middle, and I'm getting something back. Let's select them all. And now I'm basically getting one table that contains results from both. Things to mention is when we're doing the union, duplicate rows are being eliminated. So for example, if I had a product that had days to manufacture equals 1, but also color is black, I would get it in the first table, and I would get the same product in the second table as well. Now when I'm doing union, theoretically I should get 2 rows back because it's been in the first selection and the second selection. But union basically eliminates all the duplicates. I only get one result back, only one record back. By the same token, the number of attributes and the attributes that I'm selecting has to match. So for example, if I put color in here, and if I put days to manufacture in the first query, so that runs fine, and we can see that days to manufacture is 1. And then for the second one, because I'm interested in color, if I put color and run that, it's also fine. But if I try to join them together, it's actually gonna work, I think. But just to make it fail, put color as well in here. If I run it, it tells me that I can't run it because the number of attributes doesn't match the number of attributes in the second query. The number of attributes in the first query doesn't match the number of attributes in the second query. If I then run it with the exact same number of attributes, it should actually work. No, it doesn't work, but again, if I try to run this query with the exact number of attributes, but with a different data type in it, for example, days to manufacture is actually integer, and the color is varchar, it tells me that there's a conflict of data types. There you go. In fact, what it's trying to do is trying to convert color to integer. As you can see, it's trying to convert black to data type int. It's because it actually met the integer in the first query. But we can actually cheat on this, and we can say, okay, cast varchar 64, for example, and that will run fine. Okay, so the next thing that I wanted to look at is intersect. Intersect is pretty much exactly the same as union, but we only return the rows that are in both data sets. So again, if we run exactly the same query, where the days to manufacture from product equals 1, we get some data, and then we intersect it with a second query where color is black. So we get two sets of data, and then intersect will only produce the data which are in both tables, in the both selections that we've done. So in the first selection, we've got the product 680. That actually is in 680 on the second line. So in this case, we're basically getting all the products where days to manufacture is 1 and color is black as well. So instead of union, if we just put, let's delete this gap here. Actually, let's leave that. And instead of union, we put intersect. How do you spell intersect? Hey. Okay, so if I run this, I get nothing back. Why is that? Interesting. Oh yes, of course. Okay, so in this case, intersecting all the rows in the first table and all the rows in the second table, and only if they match, I'm going to actually get the result. This is the reason why actually, if I revert it to what it was before, that's days to manufacture to 64, and then here I'm just going to output color. I'm going to get no records back because the first query actually returns dataset where I've got days to manufacture equals 1, and the second one actually returns me dataset where attribute 4, which is color, equals black. So 1 does not equal black, so it doesn't return anything. Right, so that's intersect. And Cartesian product we already looked at, but we're going to look at it again, but from actually running it against the some data table that contains some data. So again, we'll look at Cartesian product a little bit more in details from SQL perspective. So here's a list of products that we've got, product 1, 2, 3, and 4, and then we want to join it to a name of the manufacturer, I think. No, actually it's a location. So we want to join it to a location, but what we want to get is each single location from a location table for every single product. So we're doing a Cartesian product, which is basically a cross join. And what's going to happen with this when we're doing the cross join is we're going to take a first row out of first selection, and we'll join to all the rows on the right hand side, on the right selection, and so we're going to get 3 rows back. So product 1 contains, has got 3 different locations. We're going to take the second one and join it to on the right hand side. We're going to get all the products with for all 3 locations, and then we're effectively joining them together, and we're getting the table that contains all the rows, basically all the products from the right hand side multiplied, from the left hand side multiplied by all the locations on the right hand side. So basically that's exactly the same as Cartesian product, and it is basically a Cartesian product from relational algebra point of view. So if we then look at the next example, instead of typing stuff on, I'm just going to take one query that I already prepared, and effectively what I'm going to be doing is I'm going to be selecting from product and cross join it to the product location, and we'll return, let's arrange this query properly so we can see what's actually happening. We'll return product ID, product name, and location name out of that table, out of those 2 tables. And effectively, I'm getting each single location for each single product back. To kind of match it to what I had in my example on the slide, I can also condition it. You can actually say where product ID equals 2 or 1, and names are only in this set. So we get exactly the same kind of result as we had in the slide. So that's Cartesian product, but effectively it's a cross join. Instead of writing cross join in SQL Server, well, basically in SQL or Oracle or MySQL, the standard definition for SQL is just basically comma delimiting all the tables that I want to select data from, and that's exactly the same thing. So comma delimited, and the order in which we actually execute them is the order in which we're going to position them in that from clause is the order in which we're going to be basically joining the tables. Again, quite important from performance point of view or performance point of view. It's quite important to know in which order you have to put the queries in, because that's the order, the preferential order for the execution to actually happen on those tables. So, for example, if I revert this order, if I take product location and stick it first, what's going to happen? What do you think? Pretty much yes. Exactly that. That will happen. So we take every single location and then we match it to every single product in that data set. So effectively, it produces kind of exactly the same result in this case, but if we did it in a whole set of table, we're going to get a very different result out of that. Actually, we're going to get exactly the same result because it's a Cartesian product. It's exactly the same thing, just reversed. But when we actually put in some conditions on it, or then join into other tables, then there might be some difficulty. Okay. Join operation is called basically a binary operation in relational algebra. Basically, selection and projection is unary operation because we only run it on the single relation. Whereas join, union, intersection, division, etc., all those operations are called binary operations because we normally involve two relations and we somehow joining them together by some kind of key. So join operation is one of the most difficult ones to get right in the relational database management system because it involves a lot of kind of optimization techniques. And the join operation itself, just a straight theta join. Theta join meaning that we're going to take one selection, and then for each row out of that selection, we're going to match it to another, basically another relation. The reason, well, basically, join itself is a derivative of a Cartesian product, if you think about it. And we're going to look at it in more details, but effectively it's doing underneath, under the bonnet, it's doing exactly the same thing. It takes all the rows out of one table and all the rows out of the second table, effectively, and then matching them up together. And then based on join, it only retrieves the data that you need. So if we look at the relational algebra point of view, we've got relation 1, and we want to join it to relation 2 by some kind of function, by some kind of formula. So that formula might be those two fields that we want to match together. And again, because we're saying that this is a derivative of a Cartesian product, we can write exactly the same join as a function of a Cartesian product, where we basically getting a Cartesian product out of relation 1 and relation 2, so merge those two tables together, and out of that Cartesian product, we're going to specify a function. I want to return, basically, I want to restrict that result set only where specific conditions are met. For example, product ID from first relation equals product ID in the second relation. So, first of all, let's have a look at Cartesian product version of join, where I'm going to cross join product and review together, those two tables. And then in the condition, in the where clause effectively, I'm going to put where product ID equals review product ID. Again, so instead of typing that in, because I'm lazy, so this is what we're going to do is we're going to select those two fields, well, two attributes from product table, cross-join it to product review table, and return review name, and rating from a product review table. But also, we just run it as that without any kind of condition. What I'm going to get is a review that is not related to the actual product we reviewed for every single product. So we've taken all the reviews and all the products and put all the reviews against every single product. But if I specify a basically if I specify a formula for restricting that result set, and I say only where product ID from a product equals review product ID. Now I'm getting only the products that have the review related to that product in the result set. Again, just to demonstrate it again, if I then select product ID from, actually I already selected product ID from product, if I select product ID from review itself, if I run just Cartesian product on it, as you can see, the first row here, product ID is 1, then I've got the name, then reviewer name, and the rating is 5, but it's actually related to a different product. So those three records are not related to this record. However, if I then run it with the condition on it, which means that I'm going to eliminate, which means that SQL Server effectively at the back end on the bonnet, what it's going to be doing is going to be scanning through every single row in this Cartesian product, going 1 equals 790, nope. This equals 879 equals that. I can actually go all day like this. And when it has a match, it will only return that row. So effectively 709 equals 709. Here's a row. Okay, so I can do pretty much exactly the same thing, but in a more kind of coherent way. So in SQL Server, we've got some useful useful operations that's been put in SQL language itself, if we can call SQL a language, that will instruct our database management engine to specifically say that this is a join. Right? If I'm doing the Cartesian product and then doing the basically a predicate on it, SQL Server might not interpret it as as a join. It just interprets it exactly as we said. We want all the data out of one, Cartesian product on the other table, and then do some kind of post selection on it. But in relational algebra, we actually have a concept called join, and it's been put there specifically to instruct the database management system that this is a join to another table. And it's written pretty much exactly like this. So we've got a product joins to review by a specific formula. So where product IDs match. And we can, in SQL Server, we can write it exactly the same way. So select from product, product name, product ID. Then in a join, this is what actually specifies our basically join. And inner specifies just a normal join, basically. So to product review, where review product ID equals product ID. And effectively, I'm going to get exactly the same data back. Right. So the next one is called left outer join. A left outer join allows us to select data from relation 1, and basically in the case of inner join, when we do an inner join of relation 1 to relation 2, then we're only going to get the records that are matched. So if there are no, for example, product reviews for a specific product, we're not even going to see it. So pretty much like the result we're going to see here. So we're selecting out of product 1, relation 1, which is product, and then we inner join into reviews. If there is no match, we're not going to get any data back. But left outer join allows us to basically select all the data from the left-hand side And that irrespective whether it's got some data on the right-hand side, we're still going to select everything from the left-hand side. And when there is a match, we're going to basically produce a match record. If there isn't, we're going to produce a null. So if I put left outer join here, then what we're going to see is that all the products are being returned. And where there is a match for a product review, where there's a product that has a review, we're going to see its review. Surprisingly, well, not surprisingly, we can do right outer join, which means that we're going to select all the reviews, and if there's a product for them, then we do exactly this. So basically that, in this case, produces almost the same result as a inner join, because basically there are less reviews than products, effectively. Okay, and left outer join is basically in relational algebra is exactly the same as inner join. So we've got product, and then review, just a different sign, and we've got a function underneath that as well. Right? So it's all cool to know how how it actually treats all those queries. But the reason why we're even talking about this and not just basically showing you, hey, this is how you select the data out of the database, and here's a table, and here's a bunch of fields, so that you can get an idea of what it actually is doing underneath. And what it's doing underneath is executing this query. So I'll just run it. So what's happening on the SQL Server Management, well, basically on the relational database management system side of things, it takes this query and then it interprets it. It interprets it in the way that it has to basically read some data out of a data file. It then has to do some matching, then has to do some string comparing, all this kind of stuff. So this is effectively meaningless to the relational database management system. It's meaningful to us, so we can effectively program it. So SQL itself, as you can see, is not a procedural language. It's, what is it? If it's not procedural, then it's what? Anybody? It's non-procedural, I suppose. So it means that we're basically abstracting all this stuff. So we don't really care about the order of execution, etc. All of those things are being taken care of by the database management system. And we can actually see what's actually happening. If we run any kind of query, and then in the specifically in Microsoft SQL Management Studio, we can say include actual execution plan right here. And if we rerun it again, see a new tab there called Execution Plan. This is a very useful tool, and basically that tells us exactly how SQL Server executed this query. And what we can do, it's kind of represented graphically. So from here, we can look at, first of all, it's done 2 scans on tables. So those things we can call scan. So first of all, if we just move the mouse over it, we can see this is a clustered index scan on a specific table, on a specific relation, and that relation was product review. The reason why they are kind of together is because they have, the scan happened on them in parallel. So it didn't do one operation, then another. It's done both at the same time. So it did a scan first, and basically, in this case, actual numbers of rows, it took 4 rows out of that database, out of that table. And if we look at index, well, the next scan, the other one, it's called index, cluster index sig. Cluster index sig is basically was looking for, and if we look at the object. No, I can't move the mouse there. But if we look at the object underneath that, it's right about there, you can see that's the relation that has been scanned. We can see the number, the outputs. Again, if we start actually breaking that down in the relational algebra, we've taken the object, we did something to it. So this is our subject. There's no predicate at the moment, so we're just basically taking all the data out of it. We've got output list, which is basically equates to our projection. And then we've got sig predicate as well. And you can see that sig predicate is, what does it actually do there? Yeah, sig predicate is a condition of the first table as well. So, but in this specific case, it's just a pointer to the fact that we have to get all the rows out of the first table and all the rows out of the second table. And effectively then, you know what? It's actually executed this query differently to when I run it. So that's why I'm so confused. All right, then it's doing a nested loop, which means that it actually joins them together. In fact, what actually happened here, which is different to when I run it, and I'm going to show you how I run it in the first place and why it was different as well. Instead of doing a full scan on the first table and a full scan on the second table, it was scanning all the products, basically all the product reviews first, and then matching all the product review IDs to the products themselves. Because this is an inner join, effectively, because it ran this query before, it estimated that would be the most cost inexpensive way of doing the scan. To do the scan first on the data that contains less rows, and then join it to the data that contains more rows. And because the first table, which is our product table, contains a clustered index, which means the data is structured and indexed properly. If we have less data in the reviews, which only got 4 rows, we can just select those 4 rows and then go to the clustered index and find those matching products to reviews instead a lot quicker. But if I then open up another query, although this query is cached at the moment, so it's probably not going to even produce the same result as I wanted. But if I run this stupid thing here, which is a Cartesian product, which kind of achieves exactly the same result, where we're going to take all the products, all the reviews, and effectively then join them together by product ID. I'm going to go and include actual plan. Hope it's going to execute it differently. No, it didn't. Damn it. Let's see if that's going to help. So this update statistic is probably going to dump all the table information, and hopefully that will basically get our execution plan executed differently. Okay, that's basically that's always a bit of a problem, actually. For example, in my case, what happened when I ran the cross join without the inner join to begin with, it did the full scan on the product table and the full scan on the review table. And then it did a hash join. Hash join meaning that it actually basically hashed the whole table first, both those tables, and then did the hash join, which is more expensive than doing it the way it did now. But because then I ran the inner join I think it included the execution plan for update stats. It did. Okay. Yeah, still a nested loop. To be honest, if you run the same query, in the same order, but you execute if you include the execution plan the first time you actually run the cross join, you'll see a very different result there. You'll see the fact that both tables have been fully scanned, and then the hash join has been performed. But in this case, because I already executed those queries, the execution plan has been either cached or a better one has been worked out by SQL Server. But in effect, you can still see what's actually happening. The fact that it scans the whole table, gets its results, and then it scans the second table and then merges them by a specific predicate. In this case, the predicate being kind of in the reversed order, even when I actually forced it, the fact that the product will be first and then review would be second. This SQL Server thought, it is a better way of doing this and actually reverse the order for my specific case. To show you a different execution plan, what I wanted to do is, obviously we can do multiple joins like this. Let's look at this execution plan. It's a little bit different. And again, we're basically doing exactly the same thing as we had in the previous query, where we scan in both tables. Then in addition, we're then basically joining them together, so we get in this result first. again, if we kind of break that down with relational algebra, we can go and specify every single scan and every single part of the execution plan as a relational algebra. Then we're doing another scan on this product inventory. So we're first joining product to product review, and then doing a product basically inventory scan, and then looking for all the, as you can see at the bottom there's a SIG predicate, which means that this is basically our condition by which we actually search and stuff, and the scalar operation of product review and product matching. And then again, we're joining that together when we're finally selecting this stuff out. When we have very complex queries, then those execution plans are very useful to estimate, so you basically understand how our SQL server actually interprets the commands that we're giving it. And this is a really good way of actually optimizing the queries. Actually see, but in this specific case, for us at the moment, it's very useful to see how it's actually performing the things that we ask it to do. That's about it.